In the last lecture, I spent the whole lecture showing the proof of positive real lemma. But throughout the proof, I kept talking about the definition of positive realness and the definition of the matrix situation for positive realness and so on. So, I would in this lecture initially try to spend time and give a sort of a better idea about what this definition of positive reality, especially for matrices, are. Now, as far as the positive, as far as the definition for positive realness for matrices are concerned, I will be following what is given in the book by Khalil. But as I was saying earlier, for the scalar case, there is no real agreement about what exactly is the definition of positive realness. So, what I would do is I would just revisit what I had said about positive realness, and I would start with the scalar case, and then I would give you the definition for the matrix case, and motivate what are the advantages and disadvantages of the equivalent definitions which are there for positive realness. So, let me start by revisiting what the definition of positive realness is. Okay. So, given a transfer function g of s, one definition for positive realness is you look at the Nyquist plot. And if the Nyquist plot lies in the first and the fourth quadrant, so if you have a Nyquist plot which looks like that, for example, then that transfer function can be called positive real. This is one particular definition of positive realness that you could use. So, if the Nyquist plot is in the first and the fourth quadrant, then you call it positive real. Okay. And some time back I had given examples of transfer functions. So, this is single input single output case. So, it is some polynomial divided by some other polynomial. Okay. Now, if you look at the theory of Nyquist criterion, then you know that if the relative degree, that means if P is a degree 3 polynomial and Q is a degree 4 polynomial, then the relative degree is 1 or minus 1 depending upon your the way you want to look at it. Basically, only if the relative degree is 1 or 0 can you expect to have the Nyquist plot restricted to this half. The reason for that is because if the relative degree is more than 1, then it turns out that the angles that for example, if the denominator is 2 degrees higher than the numerator, then what would happen is finally it would the Nyquist plot would enter this quadrant. So, one observation that you have for single input single output case is the Nyquist plot is restricted to this half of the complex plane if and only if the relative degree is 1. Okay. Now, even if the relative degree is 1, we still not guaranteed what we want as far as the positive real lemma is concerned, and the reason for that is several. Okay. So, let us just take this definition that GS has Nyquist plot in quadrants 1 and 4. Okay. This is the same as saying G of j omega plus G of minus j omega is greater than or equal to 0. Mind you, in this particular case, I am thinking of GS as a single input, single output case. So, it is some polynomial divided by some other polynomial. And so this one is greater than or equal to 0. Yeah, so that means when you evaluate the transfer function along the imaginary axis, that imaginary axis, the image of the imaginary axis lies in the right half, of the complex plane. Okay. Now, of course, we have this map from the complex plane to the complex plane, and what we are saying is that the image of the imaginary axis is something that lies in the right half of the complex plane. The image, I mean, this map here is GS. So, any point S here goes to GS there. Now, there are several examples of such things. So, for example, if you use S plus 1 by S plus 2, this transfer function, when you look at this map and you look at where the imaginary axis maps to, that will lie completely in the right half. If you look at minus S upon 1 minus S, this was also an example that I used earlier, and if you look at the map, if you take GS to be minus S upon 1 minus S and you look at the map, then again the imaginary axis will map to something here. Yeah. So, for example, in this particular case it will map to something like that. Okay. Now, if positive realness definition is just taken to be this, then both of these will turn out to be positive real. Now, if you take the state space representation of this, state space representation of this, and try to use the positive real lemma, the positive real lemma will be applicable to this only because it's the denominator has its roots in the left half plane, whereas in this case the denominator has its roots not in the left half plane, but in the right half plane, and so you cannot apply the positive real lemma. Earlier I had also talked about idea of dissipativity and idea of storage function. So, in both these cases you will get a storage function. The only difference between these two is that in this case you will, because the denominator has all its roots in the left half plane, that means this is a stable transfer function. Therefore, in this particular case the storage function that you get is positive. On the other hand, in this case also you can construct a storage function, but this storage function is not going to be positive, it is going to be negative. Now, in physical systems, if you are talking about storage function, it's some function which stores energy. Now, if you are going to look at a function that stores energy and that function is negative, that does not make sense. I mean, what does it mean to say that the amount of energy stored in the system is negative? Yeah. As a result, it does not make sense in this particular case, though you can still find a storage function, whereas it makes sense in this case and you can find a storage function. So, in both cases, so as soon as this equation is satisfied, you can find a storage function, but it is only when the transfer function is Hurwitz that you can find a storage function which is positive, whereas if it is not Hurwitz, then you can find a storage function, but that will not be positive. Okay. Now, if you look at this further, that means instead of just looking at it this way, if you put the condition that G s plus G of minus s is greater than or equal to 0 for all s such that the real part of s is greater than or equal to 0, that means instead of just looking at the imaginary axis, you look at where this whole half plane maps to under Gs. Okay. And this whole half plane should map such that it falls in this right half. If you put this added condition, then because the imaginary part is in the boundary of this thing, that means if the condition is, this condition is satisfied, then this condition is automatically satisfied. Okay. but there is something more satisfied. That means, whatever is here now gets mapped to the right half plane. Then in that case, this function, for this transfer function it would be all right, for this transfer function it will not be all right. So, if you take this transfer function and see where this right half maps to, what you will get is this whole area outside the curve. Okay. Of course, what that means is some of these points get mapped to points here, which is not in the right half, but in the left half. Whereas, if you had taken s plus 1 by s plus 2, then the imaginary axis would have mapped to a curve, and the right half would have mapped to the inside of the curve, which means every point here on the right half is going to get mapped to the right half plane. And so, this equation captures the fact that this is satisfied, plus the storage function is positive. And therefore, in some sense this should be the real definition of positive realness. Yeah. But for historical reasons, this is usually given as the definition for positive realness, and there are some places where this definition for positive realness is used. But if you give this definition for positive realness, then such functions are also permissible, and to disallow these functions, the additional condition that is given is this condition holds plus g of s is stable. And as it turns out that these two conditions together is equivalent to this condition. Yeah. So, the various books that you go through might have some mixture of these definitions as the definition for positive realness, and this is for the scalar single input single output case. And I mean, depending upon your taste, you can adopt any one of them as what you would believe positive realness to be, but they all roughly say the same thing, but there are these subtleties that need to be handled. So, let me now give you the definition for positive realness as far as matrices are concerned. Okay. So, let us assume G of S is a P cross P transfer function matrix. Okay. Now, of course, in all these cases this matrix, the transfer function matrix, has to be a square matrix because the number of inputs have to be equal to the number of outputs. So, G of S is a P cross P transfer function matrix. Then the following conditions have to be satisfied for GS to be declared as a positive real transfer function. So, G of S is positive real, and this particular definition that I am using is the definition that is given in the book by Khalil, Nonlinear Systems by Khalil. So, just like what I said in the 1D case, here also in the multiple input multiple output there could be other opinions, but I am just sticking to this for now. Okay. Is positive real if, number one, the first condition is poles of all elements in G of S are in the left half plane. That means every element, so every entry of G of S is a transfer function, and every one of those transfer functions is Hurwitz, is stable. Okay. And the second condition is for all j omega, I mean imaginary, purely imaginary value, where j omega is not a pole. So, where j omega is not a pole of any element in GS, G transpose of j omega plus G transpose of minus J omega is a positive semi-definite matrix. So, this condition is precisely like the Nyquist plot condition in the single input single output case. Okay. So, what we are saying is for all j omega, where j omega is not a pole, if j omega was a pole for some entry in the transfer function matrix, of course, then this thing will not be very well defined and there are problems. So, you remove all those omegas which might on the imaginary axis, which might be a pole of any one entry of g of s, and for all the others you will have this. But of course, remember these are matrices. So, the sum of these two matrices one is claiming is a positive semi-definite matrix, a positive semi-definite matrix. Okay. And there is one more condition. The third condition is that any purely imaginary, so any purely imaginary root or rather pole, purely imaginary pole of g of s is a simple pole. Okay, is a simple pole. That means it does not have multiplicity greater than 1, and the residue so the way you obtain the residue is limit s tending to j omega of s minus j omega times g s is positive semi-definite Hermitian. Okay. So, there are these three conditions. So, the third condition is that for any purely imaginary pole of Gs, so any purely imaginary pole of Gs is a simple pole, and the residue limit as you tend towards that pole of this particular thing, that residue of course, here is it is a matrix. So, it is in fact a positive semi-definite Hermitian matrix. So, the definition for positive realness is this. So, now if you just specialize, you take Gs to be a 1 cross 1 transfer function. Well, the poles are all in the left half plane, well, as we had said before, and this is the Nyquist condition, Nyquist criterion condition. So, the Nyquist plot in the first and the fourth quadrant, and this one is the stability. So, these two conditions are what this is an additional condition that appears in the matrix case. In the scalar case, this is clearly true, but in the matrix case it is a bit more involved, and therefore, this condition makes its appearance. So, this is the definition for positive realness as far as matrices are concerned. And so, now if you take a G cross G, P cross P transfer function matrix G of S, and you want to talk about it being positive real, you put these things, these criterion in, and you can check whether it is positive real. And in the earlier lecture, when I talked about the positive real lemma, well, there Gs could just be taken to be positive real with this definition, and as far as the realization is concerned, whether it is single input single output or multiple input multiple output, the realizations would be in terms of those matrices, and so that matrix condition would remain unchanged.